Okay, so let's start. So this habilitation à diriger des recherches, en français dans le texte, les forges stellaires, will be discussing about the research that I carried out in the last 7 to 10 years, focusing on the mostly supernova remnants, but also a compact object, a pulsar and pulsar wind nebulae at different wavelengths. I've studied those objects across the spectrum, and but mostly in X and gamma rays, and this is a collection of pictures of some of those objects that we will see in the presentation seen from the X-rays. So first I would like to thank, so the work that will be presented here is the effort of many colleagues, and I would like to acknowledge also first the help and the work that I've carried out with several young colleagues from master, PhD, and postdocs. Adrien is here, and I see other people that I work with that are connected to the Zoom meeting, and also many other colleagues throughout this last 10 years here at Saclay, at APC, Meudon, people in Montpellier, in Bordeaux, in Toulouse, in Strasbourg, and all the members of the different collaboration, HES, Fermi, CTA, and Athena that I've worked with in the past years. So in these different collaborations, I've worked at different levels, and currently I'm in the CTA collaboration coordinator of the Galactic working group since March this year. And in CTA, I'm also an active developer and part of the steering committee of GammaPi, a science tools candidate for CTA that we will discuss briefly afterwards. And in the X-rays, I'm involved in Athena, in the science advisory team, in the science center, instrument science center, and also in some European project to develop new tools for the X-ray analysis of new and future telescopes. So moving on to now the science, we will discuss here supernova remnants and pulsar wind nebulae with this presenting some context of what we can do with those objects and a selection of the works I've done in the last decade or so. So I will start with this nice movie that illustrates the role and what a supernova remnant looks like in X-ray. So supernova remnant, they provide kinetic energy, heat, heavy elements, and cosmic rays into the ISM. They have an important role in the galactic ecosystem, in the chemistry in the galaxy. And this is an example seen in X-rays of a young supernova remnant seen in 16th century by Tycho Brahe. And it's a type 1s supernova. And this is a real movie of real data. This is not a simulation seen in X-rays over 15 years. And you can see that's one of the rare objects where you can see really the evolution on a decade or so, where you can see the shock evolving rather slowly here, but we will see that the shock propagates at 5,000, 10,000 kilometers per second when it's very young. And here you can see it's evolving. And after 450 years, you can see that you reach gigantic sizes because the shock is developing very fast. So what we see here on that image is this is the ejecta distribution that is here, and we see different ejectas like of different heavy elements like silicon, sulfur, and iron, chromium, and manganese. And the blue rim that is here, this is the synchrotron emission of particles that are accelerated at the forward shock. And so with those objects, you get ideas of how the explosion proceeded, the mechanism of the explosion. You can see how the other metals are distributed in the galaxy, and also those objects are important in terms of cosmic ray acceleration. So what do we see? This is the previous one was a movie with real data, and this is a schematic view. So what do we see? We see first, so the forward shock, this is really the aftermath of the explosion, the kinetic energy, the 10 to the 51 erg kinetic energy that are injected, that are creating that bubble of hot gas. The shock will hit the interstellar material to keV temperatures. So that's why we can see them in X-rays. And there is then a reverse shock that will form at the contact of the ISM that will go inward and shock the material that was the nucleosynthesis that was processed during the supernova. And this is what is shown here as the shocked, in yellow at the shocked ejecta here. And as I said, there is this very energetic shock that is propagating at speeds about 5,000 kilometers per second. And this will, we will see that later, accelerate trapped particles and accelerate particles at very high energies in the shock. So what can we learn? So what do we see? I presented that before. What can we learn from the different components? So here I took the different aspects and try in each of those to identify what are the key science questions that we can answer. So with accelerated particles, we can try to understand by studying in X-rays and other wavelengths, looking at the rim and at the accelerated particle population, we can try to understand how the acceleration mechanism works. This is something that is still debated. We can study what kind of particles are accelerated. In order to be the main source of cosmic rays, we need to accelerate different kind of particles, electrons, positrons, and protons, and heavier ions. So we want to study the composition of the particles that are accelerated here. We also want to study the flux of particles being accelerated to see whether that can match with the galactic cosmic ray population. And also we can study until which energy those particles can be accelerated in the shock. And also, once they're accelerated, of course, to contribute to the galactic cosmic ray population, they need to escape at some point. And so this is also something that can be studied in X-rays and other wavelengths. Then in blue here, the shock will hit the gas along the way. And this can be used to answer different questions. For example, this can be used to probe the ISM properties. We have a shock that is inside, surrounded by the ISM. And so we can use that to hit the gas, make it shine in X-rays, and then we can study different properties like the density of this gas, the metallicity of the gas that is being heated. The gas that is around the supernova, when it's very young, can also give you a clue of the supernova progenitor. If you study the circumstellar material, this is the mass loss history of the progenitor star. So this gives you also an information about the progenitor. And also, I said that particles are accelerated, but of course, the acceleration depends on those local conditions, whether the gas surrounding the explosion is neutral or ionized, or whether, and the density will play a role also on that. So there is a link between what we can study of the shocked ISM and what we can study with the accelerated particles. And also, supernova remnants are one of the best examples of collisionless shock physics. And we want to study, for example, how this shock will hit the material, and in particular, the equilibrium between the electron and the proton temperature, for example. And so this is a nice laboratory to understand collisional shocks in general. Then the third point that we can learn is the ejecta. So the ejecta produced is basically the leftover from the star and what was produced in the star during the explosion. And so we can study in X-rays, they are heated to X-ray temperatures, the supernova yield. So what is the quantity in terms of mass that is produced of iron, of manganese, chromium, silicon, etc., and compare that with models of explosion. This gives us also an insight into the mass of the progenitor star. Different mass of core collapse will produce different yields of silicon to iron or silicon to manganese, etc. And in type 1a supernova, you can also use that to have an idea of the metallicity of the progenitor star. And in general, what we see in young supernova remnants, we see a map. Those are extended sources. So we can have a map of the ejecta, and we can try to have, using proper motion to have the tangential velocity and Doppler effect to have the radial velocity, you can try to reconstruct a three-dimensional model of those ejecta distribution and try to link that to the asymmetries, for example, in the supernova explosions. So you can try to constrain from the supernova remnant the explosion mechanism in the supernova. So what kind of tools can we use? So the different messengers to study all those different aspects are listed here. It's not completely exhaustive, but accelerated particles will shine through different processes from radio to X-rays to gamma rays. For the shocked interstellar medium, we can study it mostly, I would say, in optical, UV, and in X-rays. This is a thermal gas. And the shocked ejecta, it's also optical X-rays and sometimes infrared also if you want to study the dust. But this is no longer a shocked ejecta, but it's ejecta in general that you can study in infrared. So this is a little bit of the outline of this presentation, tackling those different topics. And we will discuss particle acceleration, what we can learn about the shocked ISM, and also what the remnant can tell us about the supernova explosion. So this will be a presentation of a context and a few selected publications. Then I will have a discussion on what are the tools that we can use and how can we improve them to model from a physical point of view, and also to analyze the data that we have, especially in preparation for the future observatories that are Athena and CTA. And at the end, in the recent years, I spent some time doing some outreach projects. So I have a few slides to show you the kind of project that we have been doing. So first, going back to cosmic rays, we have accelerators candidates in the galaxies, and some of the top candidates are the supernova remnant and the pulsar wind nebulae. And so in core collapse, we have to remember, of course, that those two objects are in fact one nested objects, where you have the pulsar wind nebulae and the remnant that is here. And this is an illustration of well-known supernova here. And just to tell you that acceleration in this case will take place in the forward shock, like I said previously. And in the pulsar wind nebulae, this is a picture in X-rays of the crab. We have a shock. So this is 5,000 kilometers per second. This is a relativistic shock, and it's taking place near the termination shock that is here. And we have mostly electrons and positrons that are accelerated here. And we believe that you have electrons and ions that are accelerated in the supernova remnant. And so in order to be the top candidates to explain the flux of galactic cosmic rays, those objects need to accelerate to accelerate cosmic rays and have fulfill different conditions. For example, you need to to reproduce the composition of the cosmic rays, namely electrons, positrons, and ions. You need to match the observed flux at Earth that we see of the galactic cosmic rays, and they need to reach high energy, which is the Ni feature in the cosmic ray spectrum. And so they need to be able to accelerate particles to very high energies. So how does the acceleration work? A quick summary here is that you have particles that are in the ISM that will go through the shock. So the shock is moving in this direction. And each time the particle will cross the shock, it will gain a certain finite amount of energy. And the idea is that by a repeated back and forth around the shock, you will slowly gain and gain energy. And the key thing here is how do you go back and forth? And so in order to stay as long as possible in the system, in the loop, if the first accelerated protons here, they are charged particles, and so they will influence and create a turbulence in the magnetic field that will help other particles then to scatter on those magnetic turbulence and then to come back. And the more accelerated particles you have, the more turbulent field you have, and so the more particles you can re-inject in the loop. So this is like a virtuous cycle here, and this is a nonlinear process in which you need accelerated particles to create this turbulent field, and this turbulent field is what is needed for the acceleration. So, and the next slide is a peak simulation showing this event here. So you will have a shock wave that will propagate from left to right. On the top panel, you have the density, and on the bottom panel, you have the magnetic field. And so you can see that you start with a random magnetic field. There is no strong pre-existing turbulence. And as the shock will develop and particles will gain energy, you will see some magnetic turbulence appearing here in the bottom panel. And so those are individual particles that are here. You can see this one, for example, going back and then going in. And you can see here the turbulent field that is self-generated by those particles that is here. And you can see some examples of those particles here that are arriving and then going in and going back. And this one also going in and going back. So this is and you can see that with time, you have stronger turbulent magnetic field lines that have developed, and those ones are the target for to bounce back and forth from the shock here. So how can we study that with more details? Of course, we don't have access directly to that macro scale information. And also the cosmic rays that are accelerated in the supernova remnant, once they escape, they do not travel in a straight line. And so we cannot directly observe them. So what we can do to have an in situ analysis is to look at the radiation from those cosmic rays, and across the energy spectrum, there are different processes in order to study those accelerated particles. So for electrons and positrons, you can look at synchrotron emission. They will interact with the magnetic field that is surrounding them. And from radio to X-rays, you can study that leptonic population. Then the same leptonic population, when interacting with photons fields like CMB or infrared, will produce inverse Compton, and this will radiate in gamma rays from GeVs, MEVs, GeVs to TeV. And then the only way to probe the hadronic population, so this is the protons and the ions that are accelerated, and this is the dominant fraction of the galactic cosmic rays, so we need to understand those in order to solve the cosmic ray puzzle. They only shine, mostly the easiest way is in gamma rays, from GeV also to TeV. So in the gamma ray band, you have two competed processes. You have the so-called leptonic channel and the hadronic channel. One is probing the electrons and the other one the ions. And you need, with the combination, for example, of Fermi and Cherenkov telescopes, you can see that those ones have different spectral symmetries, and having very large band analysis like that can help to disentangle between the different processes. So what we can test is, for example, the nature of this gamma ray emission, in this case, whether it's from one scenario or the other. We want to constrain the maximum energy. As I said before, you need to reach really high energies. And also the energetic of the kinetic energy that is then transferred to the cosmic ray population. And as I said in the beginning, the surrounding medium has an impact on the acceleration mechanism. So we need to understand both in order to have the full picture. So this is an example, for example, of one specific object seen at 3 different wavelengths. In radio, the image is not so nice, so didn't show it here, but what we see in X-rays is dominated by the radiation from the electrons via synchrotron that we can study with the X-ray telescopes. In gamma rays, you can have gamma rays at GeV or TeV. You can have a mix of the two processes, and the game is to try to disentangle those two components. And this can be done either from space for GeV photons or from the ground. In order to have a larger collective area, you need to go, you cannot go in space. You will need a too big instrument. And so we're using the Cherenkov effect to detect those very high energy photons from the ground with Cherenkov telescopes. So now this was for the context and introduction. So now I will present you a few selected publications that illustrate the science question that I presented in the beginning. And here, this is a series of publications that I've done here and with Chandrai Maitra here. And you can see different wavelengths of the same object. So this is a pulsar wind nebula. This is a pulsar that is here at the center. In fact, this telephone number here, this is a high E dot pulsar, 10 to the 36, and it's overlaid on a supernova remnant, Vela Junior. So it's hard to disentangle at the beginning the contribution from one or the other. So you have two extended sources on the top of each other. So with XMM here, we saw that there was a point source here and an extension here that is the pulsar wind nebulae. And with a follow-up observation, this is a zoom in this region with Chandra. We can see that it was a more complex object than previously thought, and that you have the pulsar that is here, and you have those extended lobes that are here that could be the torus, the equatorial torus of the nebula, like we see for Vela or for the Crab pulsar, for example. but it could also be some jet features as we see in Middle Age pulsars. And what is interesting is that with both XMM and Chandra observations, we managed to have an idea of the distance of that object, and it's less than 1 kiloparsec. And if you make E dot over D squared, the contribution of this pulsar, it's after Vela, it's the second most energetic pulsar in the 1 kiloparsec neighborhood. And so it could contribute as well to the electron-positron local excess if it is really nearby. And in radio recently, we reobserved that object and we discovered these bow shock, probable bow shock structures. And there are not a lot of pulsars in which we see bow shocks like that. The bow shock is due to supersonic motion of the pulsar in this direction. And this is the bow shock in the interstellar medium. And with the opening angle of this bow shock, you can have an idea of the velocity and the medium of the interstellar medium surrounding it. And from the X-ray geometry and from this jet or torus, we can also have an idea of the inclination angle of the system. And this could, our modeling here could explain why this, no, it's the opposite. It's radio loud and gamma ray quiet. We do not see it in Fermi, but we see it in radio. And this could be due to the inclination of the spin axis with the line of sight. So then moving on to composite supernova. So remember that those are Russian dolls in which you have the pulsar, the P-win, and then the supernova remnant. And such, there are some objects in which we see all of those features at once. They are called a composite supernova remnant. And this is a very nice example with this radio map where you see the shock of the supernova remnant. There is a pulsar that is here with this X-ray image. You see the compact source here, and it is probably moving further away out of the supernova remnant. And you can see the bulk of the radio nebula that is displaced because there was either the proper motion of the pulsar or also a reverse shock effect going back inside from one side preferentially. And so in those kinds of objects, what is nice is that in theory, you could accelerate electrons and protons at the supernova remnant shock. And in the nebula, you could accelerate electrons and positrons. And the galactic cosmic ray spectrum is composed of that. And so this could be an all-in-one accelerator where you have all the different species that are accelerated in this same object. With Justine Devin, we carried out this kind of study with the Fermi-LAT in order to try to see what was the gamma ray emission nature from this object, whether it was coming from the shell or the P-win or both. And you can see here that a nice example. So in faint blue behind, what you see is the supernova remnant, the same radio map that is here. And all those circles here are the centroid of the gamma ray emission in different energy bands. And you can see that if you look at the cross as a function of energy, the position, the centroid shifts towards the P-win, more or less. And when you look at the spectrum, this is the spectrum from just the shell. And you can see that it's rather flat at 1 GeV and then falling, and that the P-win component has a harder spectrum, which is what we expect usually from P-win and from supernova remnant emission. And when modeling the supernova remnant emission, those are the green dots that are here. This is the hadronic in red component. And you can see that you can reproduce the observed GeV points with a hadronic model, meaning that in the GeV emission, at low energy, we are dominated by accelerated protons from the shock. And at higher energy, we are more dominated by the more energetic electrons radiating through inverse Compton. So this is a nice example in which it's rather small, so it's hard to resolve, but this shows that it was possible at least to localize the gamma ray emission, but a composite supernova remnant in which we see both of those emissions. So in Fermi also have contributed to the supernova remnant catalog, in which we looked at the GeV counterpart of all the radio supernova remnants that are known, about 300 in the galaxy. And only a handful of them were detected in GeV, but they are shown here. And this shows the age of the supernova remnant, the estimated age. It's not always very accurate, but and as a function of the GeV spectral index that is shown here. And for the young shell supernova remnant, a few thousand years, and the ones in red in which we have evidence that it is interacting with a denser molecular cloud, for example, and typically those are 5, 10, 20 kilo years old. So those ones are slightly older, but what we see that is interesting is that there is also a shift of the spectral index between the young population and the interacting population. And one of the possible explanations is that the hadronic emission in gamma rays has a flatter spectrum at 1 GeV, close to 2, 2.5. So this is what we see above 2. And the ones that are dominated by accelerated electrons, inverse Compton, have a harder spectral index, something between 1.5 and 2. And this is what we see for that young population. So from a population point of view, it seems that from at least those objects, there is an evolution of the dominant emission mechanism as a function of age. When you are young, you are in a tenuous medium, and then when you get older, you start to touch the boundary of the cavity carved by the progenitor star. So based on that, we can draw a simple picture. It's not true all the time. I will show a few examples where it doesn't work, but a time evolution of the gamma ray emission in supernova remnants. So when the supernova remnant is very young, so for example, 87A, 30 years old, there is high density around it because of the circumstellar medium. And so you have possible hadronic gamma ray emission because the target density is high, and leptonic emission as well because you have highly energetic electrons. Then for the young ones, the ones that are that have 1,000 years, as I said before, they are evolving in a low density cavity. So the blue cavity is rather low density, 10 to the minus 2, for example. And so you are dominated mostly by the accelerated electron population, and the hadronic emission is not very high because the target of density is not very high, except maybe in some small clumps or in the regions where you will start to interact, but this happens usually more when you reach an age of 10 kilo years. Because for a massive star, for example, the wind of a massive star will carve a cavity. The cavity can be 10 parsec, 15 parsec large. And so you need to reach a certain age in order to reach the 10, 15 parsec size and to start to touch the boundary like here. And this is what we see, for example, for remnants like this one, where the gamma ray emission is here. And in green, this is the supernova remnant. And I believe the blue is the CO emission. So there is some evidence of interaction just on the boundary, but not inside. So in this nice picture, it doesn't work for all the remnants, namely Tycho that I showed at the beginning and the Cassiopeia supernova remnant. They are among the youngest supernova remnants that we know in the galaxy, 300 and 400 years old. We have measured the proper motion of their shock. It's 4,000, 5,000 kilometers per second. So they accelerate particles. But when we look at TeV gamma rays, the problem is that the PSF is not as good and the objects are rather small. We're talking about 5 and 8 arc minutes objects. So we cannot resolve them as in more extended objects. So the gamma ray emission is not well localized, but when we look at the spectrum, this is a combination of GeV plus TeV spectrum, and you can see that there is evidence for a cutoff at 1 TeV basically. And the same for Cassiopeia, this is 1 TeV, and there is a slope that is soft, and then there is a break at a few TeV. So what is causing this early cutoff? They are young, they should accelerate particles to very high energy. They are good candidates to be pevetrons, but it's not the case. And it is not fully well understood. It is possible that if you have a large scale cloud, in this region, you reduce the maximum velocity, you reduce the maximum energy, And as you have a very high density, this is what is dominating the gamma ray emission. You might have highly energetic protons accelerated here, but they are evolving in a lower density, hence they will shine less. So this gamma ray emission could be dominated by the slow shock in a way, at least not the pevatron ones. And so the problem is that they are really small, compact, 5-8 arc minutes. And so even for CTA, it will be difficult to have a really nice result image. And so in order to understand better, maybe this shock cloud interaction, is better to study larger supernova remnants, like this one, SN 1006. So this is a type 1a supernova. It is 1,000 years old. And this is a paper here in which we have studied the interaction. This is an X-ray map, and this is H1 contours that are shown here. And you can see that the shock here, which is rather circular, goes inward and is bent, probably because of this interaction region. So this is an evidence that it is not only a by chance coincidence with this H1 density, but that there is a really close encounter between the shock and the cloud. And looking at the cutoff energy of the synchrotron emission, you can see that in this specific region, the shock velocity and the maximum energy is reduced because probably the velocity is reduced. But so this is one of the nice examples in which there should be highly energetic particles accelerated nearby, and they could interact with the high density in this cloud. It is not really high, but the density in the other regions are 10 to the minus 2. And in this H1 cloud, it is probably higher than 1. So you have a contrast factor of more than 20. So you should see a little bit of that contribution. The problem is that in terms of solid angle, this is not a big part. And therefore, in the Hess map, it is really faint for Hess. So maybe it is below the sensitivity of Hess. The cloud is here, and you get a boost in the factor of 20 and density, and you see nothing here. And this is mostly dominated by accelerated electrons. So maybe it's too faint to be detected by Hess, or maybe can the protons really penetrate the dense part of the cloud? As I will discuss afterwards, there could be some shielding effect of the magnetic field in which particles cannot really penetrate inside the cloud because of magnetic field shielding around it, and therefore they cannot see the denser part of the cloud, and the gamma ray emission is reduced. But I think this is a very good case, study case for CTA, and with CTA with a better spectral resolution and a better sensitivity, and better PSF, we will be able to really study more in detail those small interaction region. So there is another object in which we can do this, this game. So this is the supernova remnant RG1713 that you see in X-rays in the image in the back. And overlay, you have the CO distribution. And on half of the remnant, there seems to be some regions of interaction between the shock and the density. And this is a zoom in that region. And there are a few clouds here. One important is the cloud C that are very massive. We're talking about a few hundred solar mass clumps, not clumps, clouds. And we believe that this one is in interaction with the shock. And with the recent deep XMM observation, we have a full coverage of the remnant. And we see here that specific clump in X-rays in 12CO, 13CO, and CS that is probing each time regions that are denser and denser in the cloud. And you can see the white contours and the cloud here. And so there is really an anti-correlation between the X-rays and the CO. And those are profile in this box, or here, this is a profile in the circle that is shown here between the X-rays at different energies in red, and the different CO tracers in the middle. And you can see that there is a clear anti-correlation between the X-rays and the CO here that is also similar here. And so there is no X-ray emission from inside. So the electrons are not penetrating. And one of the possible ideas for that is, and also in here, we tested different energy bands around 1 keV and around 5 keV. and the spectrum looks more or less the same. So there is no energy dependence of the X-ray emission. And the fact that there is no X-rays from the center of the cloud at 5 keV, where absorption from the cloud should not play a role, maybe means that there is no high energy electrons that can penetrate in the cloud deeper than the low energy electrons. The penetration of the clouds, the diffusion is energy dependent, so high energy particles should reach deeper into the cloud. But this is not the case that we see here. And this is maybe related to an increased magnetic field surrounding, enveloping the cloud. And there were some recent numerical simulations that show here a shock propagating inside here. And in here you have a cloud. And you can, this is the magnetic fields that is shown here. And you can see that the magnetic field around the cloud is wrapped around the cloud and enhanced around the cloud. And this could act as a shielding in a way of the energetic particles. And so the question is, can we expect energetic gamma ray emission coming from the center of the cloud and from the center of this cloud? And this is something that maybe we can probe with CTA, and I will show a slide at the end of the presentation. So in terms of analysis and modeling tools, what time did we started? It was the time of, it was 14:05, 14:10, something like that. Yeah, I was just looking at the time, but
yeah, about 50 minutes.
Yeah, but we started a little bit later, but okay.
Don't try.
This will go a little bit. So how to use and how to model those gamma ray emission. So mostly we have one zone models, and they don't have currently a lot of time evolution. And so together with a colleague, Damiano Caprioli, we have worked on trying to enhance the tools that we have in order to model the gamma ray emission with an analytical cosmic ray acceleration code, but with prescription from the peak simulation that they are carrying out. And this is an animation here of the SED emission at different age. And for example, you see the cooling, something that is usually not included in the modeling tools. And this is showing you the synchrotron contribution at different age of population of electrons. So this is an ongoing work, and the idea is to apply those modeling to the multi-wavelength data that we have. Then another example of tools is for CTA. There are different science tools that are candidate, and I'm involved in GammaPi, that is one of them, that really leverage on the Python ecosystem using all the tools that the astronomy community uses now. And so the code is lightweight and focuses only on the gamma ray task, and using all the other libraries for all the non-specific gamma ray tasks. And recently, there's been a publication using GammaPi to make a multi-instrument analysis of the crab paper using all different kinds of telescopes. And GammaPi, this is a workflow that I will not detail, but the idea is to go from the gamma ray-like event, the DL3 events, all the way to the science products, DL5, that are spectrum, maps, and the light curve, etc. So more globally, I wanted to emphasize on what kind of tools do we use in gamma ray astronomy or X-ray energy astronomy. In X-rays, mostly what we do is that we have an image, we draw a spectral extraction region by eye, let's say a box on this P-wind that is here. That is what we do in X-rays and in gamma ray. And then we have to disentangle the on and off contribution within the box. In Fermi, because of the larger PSF, there is a 2D, 1D spectral analysis in which you model the components as disk, Gaussian, point-like, or something like that, and you assume something for the spectrum. And then this is a parametric analysis. But the question is, should I use a disk or Gaussian, a box, or whatever? And the reality, of course, is not, the sources are not perfect disks or perfect Gaussians. And so what we have tried in the recent years was to have a component separation that will be non-parametric, and in which you assume no shape or no spectral properties, and that will separate directly based on the morphology, the supernova remnant, for example, directly from the P-wind. So, because in the traditional X-ray workflow, for example, you have a box, you have a spectrum, and then you have to disentangle based only on the spectral properties, the thermal emission from the power law synchrotron emission. And this can be highly degenerate. For example, the norm of the power law, the spectral index, depends on the temperature of the thermal component. And this is degenerate because we only use the spectral signature, whereas we could also use the spatial signature, the morphology of those two components. And you have much more information in the image that is here, because you have many pixels that in the spectrum that is here. And this is something that we can use. And so in X-ray, in high energy in general, we have the chance to have a spectroimager since the 90s, since CCDs with ASCA. And today in optical with Muse, they start to have a spectroimager as well. But we had that for a long time, but we have never used fully the 3D information that spectroimager provide. We always look at X-ray data either from an image point of view, spectrum point of view, or a light curve point of view, if you have also varying sources, and we never consider really the source. And this is an example of the Kase-Chandra data seen in 3D, in fact. And so if you look at it really in 3D, when I say 3D, it's XY energy. And this is what the Chandra data look like. And what is interesting when you look at it that way is that you directly see, for example, the emission lines from all the data. And you can also see that some part of the iron emission is in fact redshifted and blue shifted, looking at it that way in the 3D dimension without doing any processing. So I think it was about 3-4 years ago that Jérôme Bobin did his HDR presentation that I went to. And so it's useful to go to HDR presentation. And I learned about his tools that he was using for cosmology. And after we discussed, and I realized that I had the same kind of problem that in CMB. In CMB, the CMB that we want to recover is a faint component overlaid, especially in the galactic plane, with dust, free emission, synchrotron, and stuff like that. And you want to disentangle them. And in supernova remnant also, you have ejecta, shocked interstellar medium, synchrotron, and you want to separate those components. And so we started to investigate those kind of analysis and to apply them to X-rays. And so the idea, the base idea is that you can decompose your data, so XY energy frequencies in the case of Planck, into the linear sum of a spectrum and an image. And you can do that fully blindly. So you estimate A and S without no prior information. Or in the case of the CMB, you know the spectrum of the CMB very well, and so you can fix it. But it's not the case in supernova remnants. And so the output of those kind of algorithm is a sum of images and associated spectra. And in a way, we can see that as a machine learning clustering algorithm. You want to see the data points that are clustering in your X, Y energy space. And so a quick example here is that, so this equation where you have to decompose that where A and S are unknown as an infinite number of solutions if you don't have a constraint. And here the constraint in this algorithm is that the images are sparse in the wavelet domain, meaning in a way that you are looking for different components that have different morphology. Basically, you assume that the synchrotron emission in the supernova remnant has a different morphology than the ejecta. And the synchrotron usually is more filamentary on the border. So and as we will see, it works. And a quick example here where you have this image with a large Gaussian in the center and a few points otherwise. If you go in the pixel domain, you can see that it's hard to separate them. But if you go in the wavelet domain, you can see that the large Gaussian is visible at the large scale and dominating the signal, and at the small scale, the small Gaussian are dominating. And so it's easier to make a separation in the wavelet domain than in the pixel domain. So this is part of the thesis of Adrien. And he has a paper on the detailed methodology toy models that we have tested on toy models of supernova remnant. And here is the first example on real data this time, where you look at the Cassiopeia supernova remnant around the iron band. And without any prior information, the algorithm separated this into 3 components. One which is synchrotron dominated. This is the power law that is shown in blue. And 2 iron components that are shown here, one that is slightly redshifted and one that is slightly blue shifted, and that do have different morphologies. And so this is quite impressive results that we obtain, and I will show afterwards some other applications. I think it's here. Yeah, it's here directly. So this is something that we have started to look is what the remnant can tell us about the initial condition of the explosion. In other words, what can a 300 years old object can tell us about what was going on 1 second after the explosion. And the idea is that there are some traces of this asymmetry that could still be the initial asymmetries from the explosion. And the observables that we can have from the X-rays is the 3D distribution and in space and velocity of the ejectas. And using proper motion of those images with a 10, 20 years baseline and the Doppler effect, you can really reconstruct the 3D vector of this ejecta and try to compare them with numerical simulations. And so this is the ongoing work of Adrien, where we applied that not only to the iron line, but to all the lines in Casey. And for each of those lines that are shown here, we were able to retrieve a red shifted component and a blue shifted component, and you can see the associated image. And this gives you kind of a two-plane foreground and background images of the distribution of those ejecta in order to study the asymmetries. And in one word, what we learn is that most of the X-ray emission seems in the red shifted component and not in the blue shifted component. And this is compatible with what is seen with NuSTAR in the titanium-44, where they see most of the titanium that is red shifted. And then if you look at all the individual components and you plot the center of the explosion and the centroid of the image, you can see that most of the X-ray emission that has most of the mass is in the opposite direction of the neutron star, which is one of the scenarios in which trying to explain the neutron star motion due to asymmetries in the explosions. So another quick example also on the galaxy clusters, we try to apply that on other extended sources. And this is the core of the Perseus region. And with the algorithm, 3 morphologically different components were identified. And in particular, one that is very similar to the H-alpha filaments that are known in that object. And this is really the first time that we obtained such a clear image of the X-ray filaments, and for which we can have the spectrum. And if you compare the morphology in 2 different boxes, in optical and in X-rays, you can see here that they have the same width. The filament really, the X-rays and the optical are really identical in terms of size. And when you look at the spectrum, so this is not directly a fit, but this is compatible with the 1 keV plasma of low abundances, similar to the intracluster gas. And so this could be the sign that those filaments that we see here, this is not an outflow from the bright central cluster, but this is more infalling matter from the in-cluster gas that is falling into the central cluster part. So for future observatories, we have a good lineup of X-ray telescopes that are on the horizon. SVOM, so Erosita, that was launched earlier last year, which published their first X-ray map a few weeks back. SVOM, in which the CEA is heavily involved, that will be launched, I believe, next year. And then the recovery mission of ITOMI with a higher resolution spectral instrument rather soon after, but most importantly, the next large mission will be Athena in about 10 years from now, with really high spectral resolution of about 2.5 eV. And in the Athena, so this is an example of what the microcalorimeter revolution will be. This is a spectrum of the way you can see it with XMM today. And this is the same spectrum that Athena XIFU will be able to see. So you have much higher number of line emission. This is a zoom on the iron complex. And so you gain, of course, in spectral resolution, but also in effective area. The XMM spectrum was shifted by a factor of 15. And with that, what can you do? So what I was saying before is that this 3D kinematic ID, once you have a 2 eV resolution, the Doppler effect that you can measure of course, you go down to 50 or 100 kilometers per second precision in the Doppler effect. And you can study the supernova remnant yield, the progenitor, the mass, the metallicity that I mentioned before. And also for the particle acceleration, Athena will be very helpful in trying to measure the impact of acceleration particles on the ion temperature. So Athena, so CRISM will fly first. The CRIMS will only have 6 by 6 pixels. And really the key of Athena XIFU will be the number of pixels and the fact that you can do spatial resolved studies. And so really studying and having simulation of those extended sources, we need to look at how we will analyze those kind of extended sources. And so this is an example of a toy model simulation that we made using this method to produce images and spectra based on real data in order to simulate data cubes based on real data of what XIFU instrument could produce. I will skip that and go to this one. So this is a 3D rendering of what our simulation looked like. And so this is X, Y, and this is energy. And here we are just looking at a slice of 1 keV. And so you can see that with XIFU, you will be able in here to resolve all those individual lines and to see the shift effect. And for reference, this is what we see with Chandra. This is what we will see with Athena. So of course, in here, basically, you only see 2 lines. And with Athena, of course, you will resolve all the physics of those line emission. So another toy model here with Cassé to try to see the red and blue shifted and the 3D morphology. This is a toy model in which instead of 4,000, 5,000 kilometers per second, I injected 200 kilometers per second. And with this GMC analysis, because the morphology is different in gray and in red, this is what was retrieved in comparison with the truth value. And of course, we have a much better, very good accuracy, down to 100 kilometers per second. So next at higher energies is CTA. So CTA started construction in both sites, and there is already a large size telescope in La Palma in the north that got the first detection of the crab. The north one will be more optimized for low energy with the 4 LSTs, and the south will be more optimized for the highest energy with the small size telescopes. And CTA will do a full survey of the galactic plane in order to have a catalog of all the sources of TV in the galactic plane, study the diffuse emission, the population of sources, and one of the key science projects will be pevatrons. And also, really, I insist, what will be nice is that we will be able with CTA in order to really carry out the same kind of spatially resolved spectroscopy that we can do in X-rays, not at arc seconds level, of course, but we will be able to start to do that, which is still limited today with HESS. And so a quick example of a simulation of CTA, I said that in LG 1713, there is possibly a clump interaction region. So I made a simulation in which in that specific clump, the hadrons are accelerated up to PeV energies, and the rest is just following what we observe. And this is a data cube at 2 different slices. And I wanted to see whether our tool was able to retrieve and separate those 2 different morphology. And turns out that it does not do the job correctly, probably because there are maybe no statistics, and also that in comparison with X-rays, the morphology here is nothing as good in terms of physical content in comparison with the X-rays. But it was able to disentangle the source from the residual hadronic background, and this is something that could be interesting that we could test. So a word about this machine learning or the tools that we can use for high energy astronomy. So in X-rays, for example, there is really little literature in trying to do advanced machine learning tools for X-rays, because most of the deep learning, etc., are trained to disentangle dogs from cats, for example. But once you add the Poisson noise, then, and it's no longer a Gaussian additive noise, then it becomes much harder for a deep learning algorithm to separate images. And I think in X-rays, we don't have so many training samples anywhere. We're not talking about Euclid or optical in which they want to classify galaxies. We do not have 1,000 or 10,000 examples of supernova remnants in images anyway. And so what kind of tools can we use to face Poisson noise, or what kind of outputs do we want in the end? And in general, it seems that machine learning has been used for a long time in particle physics and astroparticle physics to classify the images and measure the energy, for example. But it seems that machine learning has entered the astronomy in several domains. One of them is the data-driven astronomy, and mostly this is valid for servers, for example, for LSST, Euclid, Gaia. Machine learning to classify and detect source is part of the pipeline now, but it's mostly on classification and prediction. What can we do for the so-called old school, which is object-driven? You look at one object, you have one source, but I think even in here, we can use those kind of tools, because remember that for extended sources and transient, you have a very complex data sets that is comprised of spatial information, energy information, time information. And even today with the current tools, and even more in the futures, you have a huge amount of photon lists in here. So we're not talking about one data point. And so we need new tools in order to explore this 4D parameter space. And remember that with XIFU, you will have 4,000 pixels, 3,000 or 4,000 pixels. And for each pixel, you will have a spectrum with about 10,000 energy beams. So this will produce a huge data set. And how will we cope with that? And I think we need new methods. And one of the ways to make sense of the physical outputs and how physical they can be is that you can inject some physics in this machine learning. And this is a work that we are doing with Jérôme Bobin, and in which we are trying to train the algorithm on spectral shapes, for example, power law or line emission that it is shown here, and to try to learn a metric in order to interpolate between examples. So in here, you have one line this is one line, this is another line at another energy, and you say, what will be the spectral shape for an energy in the middle? And so this is not a simple interpolation. If you do a simple interpolation, you get the green spectrum, and you need to try other metrics. And with machine learning, we came up with this metric that is learned based on the data, in which you can really perfectly reconstruct this. And the idea is to use this information and inject it in the separation algorithm. So what you get in an output has a spectral shape that is at least has some physical meaning, because it was trained on that. So on the conclusion here, so we've seen analysis based on X-rays, based on gamma rays, and X-rays constrain the environment, the progenitor, the electron population, and the acceleration mechanisms. And in gamma rays, this is the best way to probe the large fraction of cosmic rays that are ions and protons, but you need some information from the X-rays in order to constrain the surrounding medium. And also for protons to shine, they need high density, and the high density lowers the shock. And so this is a bit contrary here. But I think that interacting shell supernova remnant, like in SN1006, the two examples that I showed are very nice laboratory that we can test with the next generation CTA. And so about this cosmic rays paradigm, so we now have evidence that electrons and protons are accelerated in supernova remnants. We have indication that the budget, it's really hard to estimate the budget, but the budget is not so far from being okay. What is really missing is this Pevatron question. In young objects, we do not see very energetic events. And how to analyze everything, as I said, with current deep archives and upcoming telescopes, we need to find new ways to analyze those huge data sets. And so one of the open questions is really this Pevatron in the TeV gamma rays. We saw that those were dominated by the young supernova remnants, but for example, Kasei and Tycho are not showing this. Could they be, we see some hard spectrum sources that are unassociated. One of them here was shown recently. This is a paper from 2 weeks ago, and they have a spectrum that goes from 1 TeV to 100 TeV without a cutoff. But nearby, there is either a supernova remnant or a very bright P-wind that is very bright in X-rays and studied in X-rays. So maybe this could be the counterpart. In this case, could the candidate Pevatrons that we see be mostly all P-winds? In the galactic center, we also see a candidate Pevatron. Could this be related to some kind of p-win or several p-wins. One hope is that CTA with a better sensitivity will be able to detect the youngest supernova remnant that we know, 87A. What will it tell us? We don't know, and that will be an important clue for understanding very young supernova remnants. And in terms of explosion mechanisms in supernova, the remnant can tell us something about the explosion mechanisms using the morphology and seeing the kinematics. Studying also the nucleosynthesis yields for type 1A can give you information whether it was from the single or double degenerate channel. And if we are lucky and we have a galactic supernova, new generation neutrino or gravitational wave instrument will also give us insight into the explosion mechanism, but it needs to be, I think, a rather nearby galactic supernova. And also, last thing that I didn't mention, but in stellar physics, the role of binarity in the last decade has taken an important part. And also in supernova, there are some evidence of supernova remnant that the progenitor was a stripped envelope supernova. And in X-rays, we can study in supernova the circumstellar medium, and this can help us better to understand this stripped envelope. And also, recent searches with Gaia have been successful as finding the companion star. So where is it if it's a stripped supernova? Is it maybe a compact object or for some reason that we do not see it? So those are just two last slides about the outreach. So I've carried out with an artist different projects. This is a long time exposure of a project that was in Marseille in 2018, where we pointed at different stars. And for each star, based on the information that I retrieved for the star, there was a music that was composed individually for each of those stars. And we were looking at stars, black holes, planets, and across the night. And so what I think is nice with those kind of events is that you can bring astronomy to a different kind of audience. Because when you go to La Villette, to Palais de la Découverte, you are already bringing science to people who like science and that are familiar with science. And by going into a different area, like art installations like this, you can reach a different kind of audience and also bring science on with a different point of view. And another project that we did was for the 10 years of Fermi, where we reconstructed part of the galactic plane that is shown here with Legos, with 8,000 Lego bricks in schools. And each group of 2 students, niveau CM1, CM2, had a list of positions like toucher-couler, and they had to put each photon at one position, and then we assembled all the photons to make this giant brick that is here. And what better example of a photon than a Lego brick? Because it's really, they come one by one, and when you see them one by one, you also have the Poissonian effect when if they are randomly ordered. And so this was in primary schools and also at the Festival of Astronomy last year. And another example of project, last year we were awarded a grant from La Diagonale Paris-Saclay, which promotes art and science projects. And in here we wanted to represent the color gradient. So in X-rays we have the spectrum from each supernova remnant, and each line emission represents iron, calcium, etc. And for different objects, they have different spectra. And so we took the spectra of those different objects and made the artist made a palette of colors associated with each element. And there are some different, not paintings, but that are here. And so this is the idea here, is that you take the spectrum here, and for each one, you make a color gradient here associated with each of those elements, and you have one Jérôme behind you. You can, we will see it afterwards, but you can power it. You can power it with the plug that is here. And I think this is it. Yes.
Okay, thank you.
Thank you.